Okay, today's lesson is on rational functions, 11.4. We just finished talking about the short-run and long-run behavior of polynomials. Today we're going to talk about the short-run behavior, long-run behavior of rational functions. So the first way to talk about a rational function is to give you an example of an actual real-world problem. And if you think about what's going on in the world today with the COVID pandemic and the fact that they tried to make vaccines to help with to curb the spread, which it's obviously working. Here's an example of let's say a drug. It could be a vaccine or something like that. This is a cost equation where the cost of research, development, production is $2.5 million, and it costs $2,000 per gram to produce. Now, this looks overwhelming. It's like, how could I ever afford that? But if we look at the average cost per gram to produce this, we would take the total cost, which is a linear function, 2.5 million plus 2,000 Q, and divide it by the number of grams produced. We'll just call it Q. If we do this, we've created what we call a rational function, which is a polynomial over a polynomial. So the average cost in dollars per gram would look like the graph you see in blue here. And you can tell that we would have an asymptote horizontally at 2,000. And you can see that the more we produce of the drug, the cheaper it gets. The closer and closer it gets to $2,000 per gram. Which is kind of weird to think that, wait a minute, our startup costs were 2.5 million, right? But yet, if we produce 20,000, it's basically $2,000 per gram to produce this, even though it started out at 2.5 million. So a rational function then is just a function that we can write as the ratio of two polynomials, or a fraction of two polynomials. So we'll just say r of x equals p of x over q of x. Now, the long-run behavior, this is important, of a rational function is simply the leading term of p divided by the leading term of q. If we write it in limits, it's the limit as x approaches positive and negative infinity of p of x over q of x, or better yet, it's the limits of the leading term of p over the leading term of q, which makes things quite easy. So on this first one, if we had x plus 3 over x plus 2, that is a rational function because it's a polynomial over a polynomial. Well, if I'm looking for the long-run behavior, we know that it would be first term over first term. Well, x over x is 1. So therefore, the limit as x approaches infinity is 1. Now, why is it infinity? Because it asks for the positive. As x approaches infinity, it would be approaching 1. So similarly, if we graphed it, we would have an asymptote at y equals 1 because that's what we got for our limit. So y equals 1. And you can see that it is above the y equal 1 asymptote because the numerator is larger than the denominator. Okay, that's why the graph is above it. So there's some long-run behavior with rational functions. Here's another long-run behavior of rational functions. 3x plus 1 over x squared plus x minus 2. That's g of x. The numerator's leading term then is 3x. The denominator's leading term is x squared. So that would be 3x over x squared, which is 3 over x. Now, what in the world is that function? So we're looking for the limit as x approaches infinity of 3 over x. And again, we're looking for the positive long-run behavior. I keep failing to mention that. So guys, I'm just going to let you know that 3 over x looks like this. It's a reciprocal function. And you can take your calculators, which I would encourage you to do right now, and go to your y equals, clear everything, take 3 divided by x, and hit zoom 6, and tell me if that isn't what it is. It is. So what is this approaching in the positive direction? It's 0. Now, describe the long-run behavior of the rational function. Well, if we graph 3x plus 1 over x squared plus x minus 2 and 3 over x, we basically get the same graphs. So you can see how the leading term over the leading term basically influences over the long-run behavior, basically is the influence that makes the graphs very similar. Now here they're obviously different, but that's short run. We're talking about the long-term effect of that leading term over leading term. Now, what causes asymptotes? That's a great question. Well, the red dashed lines here on x plus 3 over x plus 2 and 3x plus 1 over x squared plus x minus 2 are found simply by taking the leading term over the leading term. So the horizontal asymptote is found by finding the long-run behavior in both directions, whether it's a negative infinity or positive infinity. So that's an easy thing, isn't it? But you can also see that we have vertical asymptotes, the blue ones. Well, what in the world is causing us to have vertical asymptotes, the blue dashed lines? We got one at -2, and we got one at -2 and 1 in this case. Well, if you recall, vertical asymptotes are going to be found when x does not exist. Well, x cannot exist when the denominator is 0. And the denominator is 0 at x plus 2 equals 0. So x cannot be -2. So one of the vertical asymptotes, I don't want to put not, is -2. Now this one, you'd have to factor on g of x. That would be plus 2 minus 1 equals 0, so x cannot be -2, and x cannot be positive 1, so it's 1 and -2. So that's how we find the vertical asymptotes. The vertical asymptotes are found by simply finding where the graph does not exist in the denominator. And we know this from way back. It's the very first thing we did this year as a group, as a class, is finding where x did not exist. And those were our domain restrictions, if you recall. These are also our domain restrictions, which make the vertical asymptotes. So your homework, that's a very short lesson, again. Your homework's on page 461. And we're going to do 1 through 16 odd, so I don't know why I didn't just put 1 through 15, but I didn't. I put 1 through 16. And then, or 1 through 17 odd, I should say, and then 17 through 23. So I want to start out with simply looking at number 9. Number 9 is 1 over x plus 2 plus x over x plus 1. We're supposed to determine the long-run behavior. We can't do it. Not until we make this a rational function. It's not yet. We need to have a common denominator. So we have to multiply by x plus 1 over x plus 1 on this side and x plus 2 over x plus 2 on this side, because we got to get a common denominator of x plus 1 times x plus 2, which I showed right here, which I did right there. So by doing this then, we'd have x plus 1 on the left side and x times x plus 2 on the right side, and then we could write it as one fraction. That's this step right here. Then go ahead and distribute. We'd have x squared plus 2x. So that would leave me with x squared plus 3x plus 1 over, and then I went ahead and FOILed the denominator, x squared plus 3x plus 2. Now, if you recall, we're supposed to find the long-run behavior. Well, that would simply be then leading term over leading term. And x squared over x squared is 1. So what's the long-run behavior as x approaches infinity? 1. On 11, it's you're going to FOIL and look at the leading term. 13 and 15, they're all ready to evaluate the long-run behavior based upon what's given. And that should help you with the graphs as well.